So we are looking at continuity now. Continuity, as I said earlier, continuity, discontinuity, limit are all closely related, right? So that limit is just the function that the value a function approaches, right, as the independent variable x approaches a particular value or number. So as x approaches a number, what does function x approach? So continuity now tells us whether at a particular point is that function continuous. Continuous functions means that a function, if we plot the graph of a function, are we going to reach a place where y will not have a corresponding value for x? For example, if I have y is equal to 3 all over 0, 3 all over x, right? I can plot the graph of this function by finding the values of x and finding their corresponding values for y, right? But if I keep substituting values for x and I get to where x is equal to 0, I'm going to have 3 over 0, and 3 over 0 in mathematics is undefined, it's not defined, right? So which means the value of y won't have a corresponding value, so there will be a gap at that particular point. It means that this function is discontinuous or is not continuous at x is equal to 0. So that is simply the idea of continuity and discontinuity. So they said giving a function x is equal to x minus 1. If the limit of function x as x approaches 1 is equal to function 1, we say that the function is continuous at x is equal to 1. What does that mean? Remember that in limits and continuity, the function, if I have this function x equals to 1, the function at a particular point might exist, right? The function at a particular point might not exist, but the limit might exist, right? So if you substitute, like when we did limits, we substituted some values and we found that the answers were indeterminate to give you 0 over 0, right? Then we have to factorize and substitute again to get it. So what that showed us was that for those functions, at those points where the function gave us 0 over 0, the functions were not continuous, which means if you plot the graph of that function and you get to that function at that particular point, it's going to give you, you're not going to have a value there, it's discontinuous at that point, right? But the limit might exist, which is why when we factorized or differentiated, it still gives us a value, which means the limit existed, but the function at that point didn't exist. So if the limit of this function x equals to x minus 1, if we substitute 1 minus 1 here is 0, it must be equal to the limit, right, of function x as x approaches 1. The limit of a function at a particular point and the value of a function at a particular point are closely related, but they are not the same. For you to find the value of a function at a particular point, you just substitute the value, that number, in that point. But for you to find the limit, you can find the limit by substituting the number, but the number with that function will not have a value at that point, so you differentiate or you factorize. But for the function to be continuous, the both of them must be the same thing. If they are not the same, the function is not continuous. That is just what we are trying to see. So we generalize that the function x is continuous at a point c if the limit of that function x as x approaches c exists and is equal to function c, right? That is it for continuity. And then closely related is discontinuity. And under discontinuity, we can look at this example. Function x is equal to this. At x is equal to 1. Now, if you look at this closely, if you substitute 1 in this function, you are going to get what? 0 over 0, which is 0. What does that show you? It shows you that what? The function is discontinuous at this point. It's discontinuous at this point, right? Which means you plot the graph of this function and you get to that point, right, where x is 1. You're not going to have a corresponding value for y or for function x. But we can find the limit of this function by factorizing the numerator and the denominator. What does that show? It shows that the limit of a function might exist, even though the function at that point might not exist. So given a function x and another number on the real number line c, as x approaches c, the limit might exist, but function c itself might not exist. That takes us to the types of discontinuity. Under the types of discontinuity, we have removable discontinuity. We are going to apply all these things in questions, but we have to understand them first. Now, when the function exists at as x approaches a particular number c, but the function at that c itself does not exist, we have a removable discontinuity. This just simply shows the numerous examples we have been solving previously on limit and continuity, where, and even on this one too, where we solve, we have 0 all over 0, which is indeterminate, and then you now factorize or differentiate, and then you find an answer. What happened there was that the function at, for example, this one, the function at 1 does not exist because it's giving you an indeterminate. But factorizing, we can get the limit. So the limit what exists, but the function at 1 at c does not exist. So this case is a removable discontinuity. Removable in the sense that we can find what, we can remove the discontinuity by doing what? Applying our normal methods, right? Which we are going to see. And they also have essential discontinuity. Essential discontinuity is what? When the limit itself does not exist at all. That's an essential discontinuity, right? And we have a special case of essential discontinuity because we are going to be looking at some functions that have two branches, a left-hand limit and a right-hand limit. So when the left and the right-hand limit exist but are not the same, that function is also discontinuous.